Thank you very much for the introduction and for the invitation. It's a pleasure. So if you have any questions, please interrupt me and just ask anything you want. So I'm Danilo, and I'll be talking about the first part of the talk, which where I'll introduce some of the foundations of deep generative models. And then Shakir will focus on some aspects of optimization and on the implicit family of generative models. So, lots of machine learning focus on classification, but there are many other things you can do with machine learning, and there are many other things you can do with probability densities. So these are just a few examples of things that you can imagine that that we want to do beyond just classifying pictures of cats. Yeah, so one very important thing is detecting surprising events, or fault detection, earthquake detection, etc. Stock market collapse, things like that. We also want to build models that have some kind of understanding of the causal structure of the world. So we want to build the models that when they see an airplane, it's not just a label and an image, but it's an object that has some properties, like it moves in the sky, it transports people, it goes from one point to another, this kind of things. And we also want to build models that have the capability to extract meaningful concepts out of raw data. So these are things that you can do with generative models. So instead of giving just focusing on a mathematical definition of a generative model, we'll define them by how we use them. So these three examples are things that we wish to do when we try to build a generative model. We want to learn a proxy to some expensive simulator. Imagine that you're a physicist trying to simulate a tokamak, and you need a supercomputer to simulate 10 milliseconds of plasma. Then if you can replace your huge simulator with a ConvNet that simulates 1,000 times faster, you save a lot of trees in the end of the day. There are many problems that involve making predictions, and predictions is basically solving conditional density estimation. And there's a lot of things under the umbrella of unsupervised learning, like extracting concepts from videos, and augmenting data, let's say in the case where you have unlabeled data and you still want to learn something from the data. So all of these things can be cast into having some way of representing probabilities in a rich manner, and approximating some distribution of the data. Here it's like just some marginal density, but you can imagine any kind of conditional density. And of course, real-world problems, they are not toy problems. They involve, in general, very high-dimensional inputs like videos and satellite images, etc. So we must also take into account the algorithmic complexity, memory complexity, etc. of these algorithms. So generative models are already widespread things in many important areas, such as industry, building products. So this is a cute example: super resolution. You can generate images, do compression, generate synthetic data to accelerate scientific experiments, or help predict new drugs, help design new experiments for particle physics, for drug discovery, etc. And also, when you think about AI in general, there are many things that are just beyond computing value functions or beyond doing classification. So there are many aspects of intelligence, such as planning, exploration, or forms of intrinsic motivation in agents, and what we call model-based RL, which is encompasses planning. All of these themes require some kind of generative model of the world around these agents. So, and there are generative models all over the place already helping these problems. So this is a very simple but important example. These are just the two condensed papers. One where generative models are used to search for new drugs. So imagine that you can show these molecules to your generative model, and then you infer some latent variables that describe the properties of these molecules, and now we can traverse this abstract latent space that it has learned by observing millions and millions of molecules. And now you can interpolate in molecule space, and now you can start exploring this landscape of molecules that interpolate in the latent space, and try to search something that satisfies your constraints. So this is about the drug discovery, for example. Another important example is to astronomy. For example, this is one example of a generative model successfully applied to the problem of detecting galaxies and very large images. These generative models, they contain learnable parts, but also they merge a lot of knowledge that the scientists have about these galaxies. So every piece of this model was built based on some physical knowledge about how light interacts with the galaxy and how light is produced, etc. So you can seamlessly merge human knowledge with these models. They are not really black boxes in the sense. So this is just, again, this very nice example of a super resolution. And this is essentially a conditional generative model. If you want, is just a problem of conditional density estimation. You're given this image and you produce this image. So it's a conditional distribution. And here in this case, this conditional distribution was learned by a GAN type of model. So of course, there are many types of model. Here is one example of what we call the pixel RNN generative model, which is an autoregressive model that is extremely powerful and flexible. And here it is generating speech conditioned on text. So of course there's a favorite application for generative models, which is producing pretty pictures. There are no cats here, but that's the goal. So these are three very different generative models that are pretty much the current state of the art in image generation. As you can see, if you carefully inspect these images from a distance, you may think there are objects here, but as you get close, you see they are no objects, and there is still a lot of the statistics of natural images that these models are missing. So there's still quite a long way to go, but these models made a impressive progress in the last couple of years. So there's another particularly important application of generative models, which is lossy compression, or can do lossless compression too. But if you think of the compression algorithm, how it works is basically you look at the distribution of symbols in your data, and you sort them by frequency, and you hash them by short symbols if they are very frequent, and you attribute a longer hash if they are less frequent. But this simple algorithm is of course very effective. Of course, it's very effective and is used everywhere. It has no knowledge whatsoever about images. So it doesn't know what is a cat, doesn't know what's a dog or a car. Imagine what would be the ultimate compression machine. The ultimate compression machine is an algorithm that will show a picture of a cat, and you can choose the level of compression where the topmost level of description of the images is this is the image of a cat. And then perhaps the next level is this is a cat with a brown fur, and so on and so forth, until you reach the lossless compression level where you're describing every pixel of the image in a lossless manner. So this is one of the things we can do with this type of models. With a very small number of bits per pixel, per dimension in this case, we can encode a lot of the statistics of the image and be able to reconstruct them with a very small amount of information. So another very important application of generative models is fast generalization. So deep models are known to require a lot of data and be slow to train. But what you can do is that you can train your model offline to take examples of a new image of unknown images and generate things similar to that. Then this is going to take a long time to train, and you're going to need a lot of data for this to work. But once this is trained, you can do instantaneous generalization in the sense that now I can show, once this model is trained, you can show examples, let's say in this case of Omniglot dataset, which is a dataset of random alphabets. You can show new examples that it has never seen before of characters that it has never seen before, and it will instantaneously produce similar characters. And of course, depending on the amount of training and test on your original data set, you have different amount of overfitting, and this is very important in this type of application. So another very exciting application of the generative models, as I said initially, is to let them discover useful concepts by themselves. So this is a very neat demonstration of that. So we train one of these latent variable models to images of random objects and video snapshots of Atari games. And then if we inspect the latent variables inside, so these models have hundreds of latent variables inside, so if you inspect these variables and you vary them individually, you discover that some of them represent very specific properties of the image. So you look at this image, it's a cube. Of course, the model has seen many millions of cubes and spheres and cylinders before at various angles. Now you show this image to the model, compute the posterior over all the latents, and then you take one of them and change it alone, while all the others are fixed. Then you realize that some of them code for things like the orientation of the box or the size of the box, or in the case of models trained in video snapshots in this case, the breakout game of Atari. You see that some of the latent variables encode for the bricks on top of the game, and some of the latent variables learn to represent the paddle of the game. So these models, as they are struggling to explain the data and at the same time compress it by the pressure of solving these two things at the same time, some of the variables will try to eventually learn important directions of variation of the data, such as the paddle and the number of bricks. So hopefully the video will load. Yeah. So of course another application is to predict videos. So here is a video of a robotic arm. So this model has been trained on many videos of robotic arms. But now it is initialized with initial condition that it has never seen before. It has bricks of different type, different color, different position. And then you just ask it to continue the video, and that's what you're seeing here. These videos are very short, but you can in principle, continue these videos for a long time. Here is the same thing with Atari. Of course, Atari images are much simpler than real-world robot arm images. So you can go much further in modeling Atari. but the same family of models apply to both domains. And this type of models are very important if you think that, for example, in reinforcement learning, you want to build agents that have the ability to form some sort of planning about how its actions can impact the future of the environment. And another batch of applications that is emerging is the fusion of computer vision, things that are lived only in the realms of computer vision experts, now with these deep generative models, which is we are starting to build models that are good enough to either replace render engines or revert them. So this is an example of reverting, learning to invert a render engine. So we have some generative process that puts objects, chooses textures, etc. And this process goes to a render engine that produces an image. And this is an example of a generative model that, looking at this image, tries to infer the individual components that make part of this image. So now these are really exciting applications of these models, and these are things that are working now. So what is making these things work? It's what we call probabilistic deep learning, which is basically the marriage of deep learning with graphical models. So deep learning is basically a set of tools to build very rich functions, which we call neural nets or deep neural nets. These deep neural nets are nothing but functions from Rn to Rn, and they are built in such a way that they exploit some domain knowledge, such as translational invariance for images, or temporal invariance for speech, etc. So, but most of the work so far is focused only on point estimates. So you see you use this neural nets to make deterministic predictions given some feature vectors. There is no straightforward manner to score these models unless you can close your pipeline cycle and you have your final metric that you want to optimize at the end of the day. The vast majority of the work pays no attention to the complexity of these models when evaluating them. As we know, we should always try to seek the simplest hypothesis that explain our data, and there's something that we're missing still when we're fitting deep learning models for data in this direction. So on the other hand, we have probabilistic reasoning and generative models that have focused on simple models because they are tractable, because you can compute expectations with them, because you can understand them, we can look inside and open them, and we understand all these coefficients inside them. And this creates a natural simplicity bias. But at the same time, these models, they are doing exactly what is missing on the deep learning side, which is they can handle uncertainty. So we have an enormous amount of theory about how to handle uncertainty and how to remove biases, etc. Calibrate your models, and as you can see, these two sides have very complementary aspects, and it is a great opportunity to try to merge them. So we're going to organize our thinking in basically three components. So one is building the models. So a model, as I said, is something that generates data, synthetic data. The learning principles. So the learning principles is what you want your model to do. You want your model to maximize likelihood, or you want your model to maximize some other laws. You want your model to maximize ad clicks. That's what is behind this. And on top of both these items, we have algorithms, which are the thing that allows the learning principle to be realized through these models. So there is a vast family of generative models, but we can start by categorizing them in mainly two types. One that we call fully observed models, which are models where every random variable in it is known. So I know every random variable that participates in the construction, in the definition of the model. So one example of that is just, let's say you want to fit a Gaussian to a bunch of points. Every point is one instantiation of the full vector of that Gaussian. It's a sample of that Gaussian. So that's a fully observed model, for example. So now we can also postulate, we can also create models where we postulate the existence of some variables that are not observed. And there are many reasons for which one would want to do this. One is to exploit causal knowledge of the problem. You have some knowledge about how things are generated, about the actual physical process that results in your data, and exploiting this knowledge with these latent variable models is a very natural thing. Now, within the latent variable models, there is a further distinction. So this distinction is not very old, but is a very simple, but it only makes sense to really do, given the concurrent families of generative models that a lot of machine learning is exploring now. So one family of models is what we call the explicit models, which are generative models, here expressed as a directed graph, where every random variable is attached to a smooth conditional density. And there's a family of models which we call the implicit generative models, which are also popularly known as GANs. And these models are mathematically the same type of objects, but we assume that the thing that generates the data has no further noise. So we have a set of latent variables, and we pass them through some deterministic function, and the output is our data sample. Whereas on this model, you generate your data, pass through some function, and that function will produce some parameters of a conditional density at the bottom, and then a sample from this density will be the sample for your data. So as you can see, mathematically, they're not very different from each other. But because of this simple difference, there is vast differences in the way that we train these models. So the family of fully observed models itself is very large, and here we focus only on one quadrant of this spectrum. So we focus on what we call directed or autoregressive generative models, such as these models in the list. And we will focus on, for example, NAID type of models and Pixar type of models. And there are many other things that you can also consider. So what is an autoregressive generative model? It's simply a model that can be expressed by this causal graph, where every variable depends on everything to the left or to the right, or you define some order in which you want to build your causal chain. So this graph has a one-to-one correspondence to this equation, but this graph alone, all it tells you is this assumed causal relationship between these variables, but it doesn't tell you much about what is the computation that you need to do to actually build this model. So this is a very interesting, very powerful notation, but it's not enough to actually instantiate your model. Now, if you see many deep learning papers, you're going to see a bunch of block diagrams like this. So we call this a computational graphs, which is almost the same kind of graph as we see in graphical models, but now they mean different things. So in a graphical model, these arrows hitting these circles means that you have a conditional distribution of, let's say, this x3 given x1 and x2. Whereas here on the right, the arrow simply means there is some computation that is performed inside this box. That is then, and the result of that computation is then transmitted to the next box and so on and so forth. So it's a deterministic computation graph. And then we can, of course, mix the two notations. So now we can expand our graphical model notation and merge them with this computational graph notation. And here, for example, is the pixel RNN block diagram merged with the graphical notation. And now we can add a little bit more details to what's happening here. Now, these blocks tell us more than this on the left, in the sense that it tells us exactly how the conditioning is happening. So in this case, the conditioning happens through the state of this RNN. So every x depends on the state, on the previous state of the RNN, which is a function of all the previous x's through the previous states. And moreover, the transitions, the state transition is specified by this box, which in this case is a LSTM network. So now we have merged neural networks with graphical models. Now, one very good example is again is PixRNN, which is a model exactly of this type to generate images, where you start at the top left corner of an image and then you go just in raster order, generating pixel by pixel. And surprisingly, this is one of the state-of-the-art generative models, in spite of this very odd way of generating images. And the part of the success of these models is because once you start parameterizing these conditional distributions by deep neural networks, you suddenly gain an enormous amount of power and flexibility to wire these things. So you can be very creative about how to exploit local information about images. We know that pixels that are nearby are correlated, etc. And we can put all this knowledge into this computational graph through the flexibility of deep neural nets. And so one advantage of this family of models is, of course, that you have the exact likelihood. So once you feed the data through this chain, you know the likelihood of the data, if you ignore the parameters for now. So they are easy to train, because you can evaluate the likelihood of these models very quickly. However, they have also some drawbacks. So one of them is that it's order sensitive. Of course, as I said, you have to choose an order in which you're going to generate your data, and this order may have a large impact on the performance. Although empirically, it doesn't look like this is such a big deal for images, you can probably imagine cases where this would be problematic. And also, generation is slow. Why sampling from these things is slow? Because you must generate them one at a time. So I cannot generate x4 if I have not generated every random variable in between. So I cannot run things in parallel, which is also part of the reason why deep learning is so powerful, because we can exploit a huge amount of parallelism in these models. Now similarly, latent variable models there is a vast amount of literature on training latent variable models, and again we are going to focus. We're going to focus on a very small corner of this diagram of models that people have been considering through history. So again, we can represent these latent models with the same type of notation. This graph means that there is implies a certain causal relationship between these variables. It means that if I want to generate x, I first have to generate theta, and then given this theta, I have to generate z, and then I can generate x. So, and there is a one-to-one correspondence between this picture and this equation. But again, as in the directed and in the fully observable model case, this doesn't specify my model completely, because it doesn't tell me what is inside these conditional expectations. So now this is one possible instantiation of this model, which is just a bunch of Gaussians in this very simple example, where these are all the parameters and the other latent variables are specified in this way. Now we can as you can imagine, as you can observe here, there are lots of deterministic computations that I'm doing with these random variables. For example, here I sample this theta, and then I compute xp of theta of the second component of theta to be the variance of this Gaussian, and I take theta1 multiplied by z and so on and so forth. So there's a lot of deterministic computation happening inside of these graphs. And that's what you can exploit with this merge of graphical model notation and the computational graph notation. So we can express the same generative model in two different ways. Here's exactly the same model, but now I'm making it more explicit the actual computations that I need to do to sample from this model. So these latent variable models have many advantages and also the disadvantages in comparison to in comparison to the fully observed models. One obvious advantage is that we can produce many samples in parallel. We don't have to wait. If you want to generate a component 100 of x, we don't have to generate all the previous components before sampling a component 100, because they are all conditionally independent given all the latent variables on top. So we can exploit a lot of parallelism and generate lots of samples per second. So another thing that's positive about these models is that they can actually fit our view of the causal relations in lots of data sets. And you can directly translate our physical knowledge about how this data was generated into this type of model. Yes, as in the example of the render engine, you can imagine someone samples a bunch of objects and then put them on the image, and then that goes through some render engine that produces an image, and you can specify such a computational pipeline with this type of relation. A problem with this type of models is that now learning will require computing the distribution of these latent variables conditioned on this variable x. And this is in general very hard and a very slow procedure. So, and that's the focus of this talk, is in methods to approximate and try to deal with this problem. So, when it comes to approximate the learning of these models, there are probably infinitely many algorithms we can consider. These algorithms, they are pretty much all related to each other with some differences here and there, but mostly they differ by deterministic approximation methods or stochastic approximation methods, or something that is in between both, where you use partially deterministic approximations such as Taylor expansions, perturbation, etc. And for the things that you cannot or you don't know how to compute expectations by hand, you use Monte Carlo or other methods of approximation. So now, So because solving this approximate inference, because of this inference issue, we cannot separate the inference problem from the model, and they typically come together. So you can see the models will come with their own inference methods. And the type of approximation you want to do will also be affected by your goal at the end of the day. So you want to compute predictions. So you want your condition of density to be accurate. So if you want to do planning, you want to have unbiased estimators of your cost functions. and there are many other applications. And each one of them will require you to focus on different aspects of the data. So now I'll go through a few important approximate inference methods. So again, this is the family of models we are considering. We assume that you have some IID data, and you want to compute the likelihood in this case. And this involves solving this expectation, which is the expectation of this conditional distribution of x given z under the prior over z. So z is very high dimensional, and this conditional distribution will have a component inside, so there's no way I can solve this by hand. And we have to approximate. There are many, many approximations we can do. I'll just list some of them. So one very well-known approximation is called the Laplace Approximation. Imagine that this is your log likelihood, this blue thing. And in the Laplace Approximation, we approximate one of the modes by a Gaussian. So as you can see, in this particular case, it would be a very crude approximation of the log likelihood. But this allows us to solve the expectations analytically. And in some applications, this is good enough. Now, we have importance sampling. Importance sampling is a very popular way of approximating these integrals, which consists in basically introducing some proposal density Q and rewriting the original expectation as an expectation under this proposal. And for this expectation to be correct, you have to introduce these importance weights. We can just rewrite this ratio, this density ratio, in terms of what we call the pointwise free energy, and we can now approximate this expectation by Monte Carlo. That is, we take a k sample from this Q distribution and approximate by a finite number of samples. This is just rewriting this f there. And we can, by just applying the Jensen inequality to this problem, we can demonstrate that on expectation, for every k, this is a lower bound to the true log likelihood. So this is an illustration of that. This is a latent model with only two variables, one-dimensional variables. This solid line is the true density, and I build the lower bound on the true density based on importance sampling. And you can see as you grow the number of samples, the bound gets closer to the true density. But you can also notice that even though this is a very, very low dimensional problem, I had to use an insanely large number of samples for these curves to look nice. And this is one of the challenges with the importance sampling, is that if you cannot learn this proposal density in a sensible way, it will scale very, very badly with the dimension of the problem. Now, Gration Approximation, it starts the same way as the importance sampling method. We build the same, we use the same trick again, and we write the expectation on proposal density. The main difference is that we exploit we apply the Jensen inequality to the log, so to this expectation, so we can swap the expectation of the log, and then we end up with this bound on the likelihood. And the reason why we do this is that typically this expectation is much easier to either solve by hand or to optimize than the original expectation that was inside the log. Now we can also rearrange these terms into two terms. One of them is known as the reconstruction term, and the other can be interpreted as a regularizer, which is the K divergence between the proposal distribution and your prior. So this thing is called reconstruction simply because it is trying to recreate x from the z that was inferred from that same x. Now, there are many corrections you can do. Once you have chosen a Q density, you can do what we call the perturbative corrections. So perturbative corrections basically amount to exploit some extra knowledge about about the strength of the parameters inside your conditional dependencies. And if you know that one of them is smaller than others, or some part of your graph has a weaker influence on the rest of the graph, so you can do a Taylor expansion around that quantity. And here I just made the assumption that the model is I just made this trick that the free energy fluctuates only a little bit around its mean. But this is just one example of how we can do this perturbation correction. And now that we converted all these nonlinearities into polynomials, now we have a series expansion of expectations. And if we ignore all corrections, we get back to the variational bound that we had originally. And as you keep adding more and more terms, we will get a more and more accurate bound. And if you could add all of them, you would recover the true likelihood. So now, when it comes to building a model, of course you have to choose the generative model, you have to choose what's the causal mechanism that is going to produce your data. And sometimes you cannot choose. For example, if you're a physicist looking at particle physics, your model is not chosen. Your model is the standard model of particle physics, and there's nothing you can do about it. All you can do is run it and produce samples from it. And this is going to be on your first simulators. But you can choose how to do approximate inference on that model. And you can choose what kind of approximation you're going to run to optimize the parameters of the model or of the approximate inference. So one very popular instantiation of the variational algorithm is the variational EM algorithm, which consists in alternating solving your approximate posterior and maximizing the parameters of your model. And you do this, this forms a sequence of fixed point equations that you keep solving until convergence, if they converge. And this can be summarized in this diagram where you first solve all the integrals, you have to solve all the expectations, and then you optimize them once they are computed. Of course, this procedure works, but it has an obvious drawback, which is now test time. If I give you a new data point, you have to run all this optimization algorithm all over again. So it's going to, this whole thing is going to be extremely slow at production time. Now, one way of solving that is to do what we call amortized inference. Amortized inference is simply replacing the argmax over the space of densities. So it's like a non-parametric inference problem over the argmax over the parameters of a parametric family of densities. And now we converted this functional optimization into a parametric optimization, which is much more amenable to standard tools for deep learning, such as gradient, etc. Now we can put all of this together, all of these ideas together into one very simple instantiation, which is known as variational autoencoder. So variational autoencoder is probably the simplest thing you can do with this building blocks. The idea, so the generative part of the model, it simply starts with a spherical Gaussian that you pass through your favorite neural net, NLP, ConvNet, MSTIM, whatever you want it to be. And this neural net will output the sufficient statistics of this conditional distribution, which in this case is a Gaussian. So the sufficient statistics is just the mean and the covariance matrix. This is your generative model. This is how it generates data. Now you can build the inference model in exactly the same way. You build a neural network that takes samples from the data, pass through a bunch of nonlinearities, convolutions, recurrent computation, whatever you want, as long as it's differentiable. And in the end of the day, that's going to produce the sufficient statistics of some density. Here again, it's the Gaussian. And this way, now I have a very cheap mechanism to produce a approximate posterior for every x. I don't have to solve any optimization at production time. And we can put all these things together and build the loss of this model as we have derived before, and this loss is the lower bound on the likelihood. And we can now optimize that with methods that Shakir will explain later. But within this family of models, there are very cheap mechanisms to optimize this loss. So, of course, the VAE is the simplest thing you could possibly build. You can now build arbitrarily complex models exploiting all possible ways in which you can merge these graphical models with the deep neural nets. You can build recurrent VAEs. One important example is draw. You can build recurrent inference networks. You can build autoregressive or structured tree-structured priors. You can, of course, the type of these models don't really care what is the underlying data. You can apply don't have to apply this to images only. You can apply to volumetric data, audio, etc. And you can use these models in combination with standard classifiers, for example, to do things like semi-supervised learning when you don't observe all the labels of your model. So just to summarize what I have said so far. So we started with many important applications to AI, science, and business of generative models. Then I spoke about a merge of graphical models with computational graphs, which so far is just a convention choice, but it's a very powerful way of representing these complicated models. Then I spoke about fully observed models and latent models. So now we also see some introduced the Gration Approximation, and one very simple instantiation of that, which is the VAE. So this is the end of this first part, and now I'll let Shakir talk about the next steps, which involve optimization and implicit models.
So given the background that we now have and sort of the principles that we have of inference and how we put them together, I'm now going to give you a few more tools and different ways of thinking about generative models. So the thing that was left out in the previous section was how you actually do the optimization, how you actually compute the gradients. I'm going to discuss this area that we call stochastic optimization, and I'm going to try and connect it to the wider set of literature, because this is an area of mathematics that we can apply to almost every problem. So particularly in the case of the EM algorithm or for variational inference, this was the setting that we had. I'll point to this side instead. We had the EM algorithm, which was first compute an expectation, then do the maximization. But now, instead, what we're going to do is try and compute this gradient more directly. So we're going to try, in some sense, to swap the order of this integration and this gradient. So there's some problem with this. In general, you won't know how to compute this expectation. This is the problem of approximate inference. And then the gradient that you want is the parameters phi, and these phi live in the Q distribution, this approximate posterior distribution. So we're going to need some kind of tools to fix that. So this is the general problem that I'm going to set up. The problem in almost all of probabilistic learning is compute the gradient of some expectation under distribution Q of some function f. The function f has parameters theta, and the distribution Q has parameters phi. And in this case, we want to compute the gradient with respect to phi. So if I write it out, there's the integral of Q times f. Now, there's only two things you can do. You can either take the gradient or do something with the measure of this distribution Q, or you can try and do something with the function f, take the gradient of the function f. So this is then going to give rise to two different classes of stochastic gradient estimators. One, when you take the derivative of the measure Q, we'll call the score function gradient estimator. And when you try and take the gradient of the function itself, then we're going to do something which is called the pathwise gradient estimate. And how these two things come about, they have different properties in different types of cases. When you will use them, we'll discuss these together. And so this same integral you will see almost everywhere you look in computational science. So obviously we showed it to you in the case of variational inference for generative models, but if you do it in reinforcement learning, the very last section, I will show you this exact same integral used to solve problems in reinforcement learning. If you are in operations research and you are doing inventory control, this exact same problem for the queuing system is going to come up. If you are in finance and you are doing a Monte Carlo simulation of the financial market, it is the exact same integral. And then they do other kinds of things like sensitivity estimation because you want to analyze a process control in a system. So this is a very generic problem to want to study and to know different ways of doing estimation. There are in general 4 rough classes of doing these estimators, but we're going to look at these 2. Because they are the most general purpose. So the first one are called score function estimators. So the score function, again, this is the problem. I need the gradient of this expectation of a function. I'm going to take the gradient with respect to phi. And in this case, I'm going to look at this thing called q. So the actual way of computing this gradient, what you do is you take the gradient into the integral. Then you start doing a few manipulations. And the gradient is then going to say, take the gradient of the log of q with respect to phi, multiplied by the function f, take it an average over all ways of doing q, and that will be the gradient itself. So it's very simple, it's just the gradient of the log density reweighted by the function. And because this function, log q, is called the score, that's why this is called the score function estimator. But again, I said you'll find this everywhere in machine learning. So in the 80s, when they introduced and developed this kind of estimate, they called this the likelihood ratio trick. I think likelihood ratio is not a great name for this. If you were doing in measure theory, you would have seen this as the radon-Nikodym derivative, which you use to do lots of the proofs. Of course, in reinforcement learning, this is the basis of the reinforced algorithm and of the policy gradient theorem. In other areas of probabilistic inference, we call this automated inference and black box inference to do this. So when do you want to use this kind of a gradient estimator? Well, whenever you don't know anything about f, when f is not differentiable or you can only observe its value, then you typically want to go and look at this kind of an estimator. Obviously, because we are going to use derivatives and we're going to compute an expectation over q, we need to be able to know this density and be able to sample from it easily. But if you can do these 2 things, then this is one of the most general purpose gradient estimators that you can use whenever you are doing some kind of stochastic estimation. The problem with this, though, is that you can typically have high variance of this estimator. So if you look at the product, there's a product of f times this gradient. Assume f is a sum of k terms. That means the variance of this entire gradient will be of the order of k. And this is something you don't want to do. So a lot of work in this area involves reducing the variance of these kind of estimates. Let's go to a different kind. This one is very popular these days in machine learning. And in this case, here's again our integral problem. And now we're going to focus on the function f itself. And the thing you want to do is to try and rewrite this integral in a different way. So what we're going to do is we're going to look to manipulate q in a different way. And if we can rewrite q as this random variable z as an invertible transformation of some other known base distribution or primitive distribution, then we'll be able to redo this. So think of a Gaussian, for example. If you want to generate any Gaussian with mean, mu, and covariance R transpose over sigma, what you'll do is you will sample from the standard Gaussian, push that Gaussian through the, add the mean and multiply by the variance, and that gives you the Gaussian you want. So that's an example of this kind of function g, which is invertible. And the base distribution in the Gaussian case is itself a standard Gaussian, but you can do this for almost every of the standard distributions we have. So in our integral problem, what you'll do is wherever you see z, you will now replace it by this function g. And because it's deterministic, we will be able to rewrite the expectation with respect to now this primitive or base distribution epsilon. So this is now the principle of reparameterization that you do. It's the first thing you basically learned when you learned about random variables. So now, after we've done that reparameterization, because we want to take the gradient with respect to phi, it can just jump through the integral, and then this is what we get as the gradient estimated. So now it's just the gradient, the expectation under this primitive or base distribution, and then this now is just backprop. You just take the gradient of f with respect to g, then g with respect to phi, and that's what it's called. So again, this is one of the oldest kind of estimators that we have in stochastic optimization. Everyone writes in their papers reparameterization trick. When we wrote our paper, we called this stochastic backpropagation because of that backprop that needs to happen here. In other areas, they will call this perturbation analysis, because you can see you do a perturbation of this gradient over the density or distribution epsilon. Affine independent inference, doubly stochastic estimation, and if you are reading more in statistics, you will call this a non-centered parameterization, which is what you use to improve the efficiency of the Gibbs sample. So when do you use this thing? When f is differentiable, because we're going to do this backprop, then this is the first kind of estimator you should use. You need to be able to sample. Q needs to have this invertible transformation attached to it. But almost every distribution has this, because we can always sample from the uniform distribution as the base distribution and use the inverse CDF, or locational scale transforms, or other kinds of coordinate transformations. But you also need to be able to sample easily from that base distribution. And in general, for functions that are not too wiggly and that are distributions that are smooth, this gradient estimator will have the lowest variance amongst their competing estimators. So this is usually the first kind of gradient estimator you will look at when you need to come to this problem. But there are a few other kinds of gradient estimators that we can use. So let's look at the problem of computing these kind of gradients when that Q distribution was a Gaussian. So if you know you can use a Gaussian because your problem tells you so, then you can exploit the knowledge that that is a Gaussian. So the first one that you will get, which we'll call the first order gradient, is exactly what the pathwise derivative said. You will know some path from epsilon, a base distribution, through to G, using this coordinate transformation, and then the gradient estimator itself is, well, this is just the Jacobian times the gradient of mu times the gradient of sigma. So this is just the reparameterization trick, pathwise derivative. But there is another famous theorem, which is called Price's theorem, and Price's theorem helps us relate gradients to the higher order properties for Gaussians. So we can come up with a second order gradient estimator, which will then, here you can see this is the same as before, but now this second term actually pre-multiplies by the Hessian. So now we actually take into account the curvature information associated with the density, and so this second order gradient will actually have even lower variance than the previous one before. So if you are happy to use this kind of knowledge, then you should use it. And you can develop low variance estimators in this case. So that's everything about how we compute the gradients. The other part of what Danilo spoke about was this distribution Q. And he didn't actually tell you much about this distribution Q, except that in the example of the VAE that we gave, it was a diagonal Gaussian. And in the more complicated versions, they were created in other complicated ways. So I'm just going to describe a little bit about the general ways that we have about building these kind of distributions. So the simple class, so this is the problem of variational inference. You have a true distribution which you don't know, and you're going to choose some simpler class of distributions Q that you're going to search in to try and find the best match, and you're going to try and minimize this variational free energy to do that. So now, how can we parameterize this class of distributions so that we can get as close as possible to the truth? When we did it for the diagonal Gaussian case, we had this fully factorized, or what we call the mean field approximation. So there's literally no dependency between any of the latent variables, and this is simple to do, especially for Gaussians. But we can do much more than this, and so we want to go beyond this kind of mean field estimation. So I want to show you some examples of typical posterior distributions in the real world. So we took some MNIST digits and we looked at their posterior distributions under a 2D latent variable. And so the gray curves are the thing you want to look at. They are the true posterior distribution. And then we trained, we used a very simple recognition model, a Q which was itself a Gaussian. And these are samples from that Gaussian are the blue curves. So one of the things you can see is that sometimes the true distribution, even in simple cases, will have some kind of tilt, as it does here. They will have some tail probabilities or tail behavior that we can't correct. And this mean field distribution, just the product of univariate distributions, usually is not sufficient. So if I give you a few more examples, it's best just to look in the last one. These are different zooms of the same distribution. Depending on the nature of the function that you have, so here's when you have sigmoids, this is what happens when you have some tan H's in the model. You can have highly correlated, things can look almost Gaussian but not quite. They can have very sharp tails which go on for very long and drop-offs in the other cases. And so real posterior distributions in the real world are not Gaussians. They have very complicated dependencies. They are non-Gaussian. They have multiple kinds of modes. So we need to find some kind of tools that actually help us do that. So when you want to build this kind of Q distribution, you're going to start, this is the spectrum of things we can look at. On one end, you have the mean field, which is the fully factorized, the simplest thing you can do. And on the other end, you have the true posterior distribution, is the thing you can't attain. So in between is everything we're going to search for in here. And so the way we will search for Q distributions here is exactly the same kind of tool and thinking and reasoning that we will use when we are trying to build a model of data itself. So everything you know about building density models, building models, that's what we will use here. But we will have two requirements for these Q posterior distributions. We will want them to always maintain computational efficiency, and given the way we want to do it with the amortized inference, we always want to be able to sample from them. So the simplest one that many people have seen, and if you've seen in some of the textbooks, are called structured approximations. And an approximation that is structured is anything that introduces some form of dependency. So you can see here it's qk of zk given some subset of other latent variables. And here you can see there's a dependency between z1 and z2 and z2 and z3. And these things, given knowledge that you have of your problem, can already help you go very far and be much more accurate in terms of your model. So here's just a whole spectrum of things you can do. Instead of just using a diagonal Gaussian, you can build far richer covariances, and there's lots of literature on building covariance models and how we would parameterize covariances if we wanted to use Gaussians. Of course, we can also use mixture models, because mixture models are the next richest thing we have. We can also build another kind of thing which we call auxiliary variable models, and auxiliary variables help us through integration couple distributions and add additional dependencies. Many of you would have worked in copulars, and copular methods are another way of parameterizing marginal versus joint distributions. And one of the other ways related to the auxiliary variables is what we call the normalizing flows, which are ways of taking simple distributions and making them richer through deterministic transforms. So this is sort of the current family, and we're just going to focus a little bit more on normalizing flows as a general tool to build these kind of distributions, and we have lots of references for all of the others. So what's a normalizing flow? A normalizing flow is a transformation of some distribution. We always start with a simple distribution Z0, like a Gaussian, independent set of Gaussians, and then we transform that Gaussian using a sequence of invertible functions. So these are the functions listed in these arrows here, and we're going to just apply this function. It's called a normalizing flow because at the end of the transform, because the function is invertible, you get a normalized distribution at the end. Right, so here's a little picture. We start with a simple Gaussian, and we're going to push this through at every set of T transformations, push it through some function f. This function f, because it's invertible, the rules for change of variables of probability apply, and we can always know the distribution at the next time point. Right, and it's always given by the product of q times the determinant of this function. So what do we have to do now? And so one of the nice properties of normalizing flows is that you can always easily know the sample from the complicated distribution at the end, because what you do is you sample from the Gaussian, and you just apply the Gaussian through that sequence of functions, and the transform variable at the end is a sample from the complicated distribution. And the entropy or the log of this Q distribution, which is one of the things you needed to know, is very easy. It's just the log of the initial distribution, which you always knew because you chose that as a Gaussian, and then you just need to sum the log determinants. So how do we actually use this in, so let me just give you a little more intuition for how a normalizing flow will work. So here's two initial distributions, a Gaussian and a uniform distribution. And we chose the functions so that they sort of do interesting things, and you apply up to 10 transformations. So you can see after one transformation, that's just maybe a simple function. You just can re-squash the density in some way. But after two transformations, you can then start shearing, pulling the distribution apart. So what was initially a Gaussian is now multimodal. And if you apply many of these things, you can get highly multimodal, highly flexible, very complicated distributions. And this was the kind of property that we wanted of, this is what we saw in real-world distributions, and why we think that normalizing flows, for example, are one way of building rich posterior distributions. Here's another set of examples based on some more structured densities. And you can see after two distributions, you can sort of get the multimodality. After 8, you start getting a bit more of the tail. And after 32 of these kind of transformations, then you can do much more. You can learn the multimodality, get the complexity, get the height of the distribution. So basically, we need to choose these functions f, and these functions f are going to be neural network, but they need to be neural networks of some special form. So this is now the free energy that we started, at least for variational inference. It's the expectation under our base distribution of the log likelihood. And then we're going to have the entropy of the initial distribution, which is the Gaussian that we chose, and then the sum of these log determinant terms at the end. So that's what we're going to do, apply the change of variables rule. But because we need to compute this log determinant and we need to compute gradients through this thing, we want to make sure that we can compute this efficiently. So there are several ways of doing this. The first one, or the simplest one, is called the planar flow. This is a function which looks like a ResNet, if you know that from other kind of deep learning methods. There are other functions which is called the real MVP, and another kind of method which is called the inverse autoregressive flow. And the property of all of these kind of transformations is that they allow linear time computation of the determinant and its gradient. And because it's linear time computation, the resulting distributions don't make it any more expensive than having used the Gaussian to begin with. And each of these add more complexity in the way they introduce dependencies in the latent variables and in the way they do mixing. And so these more complicated normalizing flows can do very well. Just a little note on what happens when you want to use these kind of normalizing flows on non-Euclidean manifolds. So often you may want to have data that's angular systems, or they live in some periodicity, or they are constrained in some way. Then you will be operating in a different space. So the principle here is to take those distributions on those complicated spaces like a sphere, project them through what's called the chart onto the Euclidean space, apply a normalizing flow in the Euclidean space, and then use the inverse of that chart to then build distributions that can be projected onto more complicated systems, so like the sphere. And instead, now the rule for change of variables looks a little bit different, and that's because the space, the dimension of the manifold space and the Euclidean space can be different, and so now we use J transpose J, which is the Jacobian. And here's another example of what happens when you do normalizing flow. So this is the projection of this space onto spheres, a torus and a cylinder, and different ways of building these distributions. So if you're doing some kind of protein folding, for example, and you're modeling angles, or you have latent angular coordinates, then you could use one of these kind of methods to do that. So here's a summary. We have the least expressive on one end, which is the mean field approximations, the most expressive on the other side, which is the true posterior, which we can't get to, but we have a lot of things in between that we can actually use, that we can parameterize very richly using neural networks to try and get as close as possible to these true posteriors. All of these methods have their own trade-offs. They have certain design things to make. You have to choose the number of mixtures. You have to parameterize your covariance models. You have to trade off space versus memory versus computational complexity. But we quite like normalizing flows right now, and it's one thing that we think about quite a bit. So, okay, I'm going to shift a bit. We looked at this class of latent variable models that had likelihood functions. And in the beginning, Danilo explained that there is another class of models which are called implicit generative models. These are models that we won't make this likelihood assumption. So this now would imply a slightly different kind of thinking and reasoning that needs to happen. So for many kinds of models, we will have only partial knowledge. We'll know the unnormalized probability, or as Danilo said, you just have a simulator of the data because it's a physical system or it's some simulator of economic conditions. And when you are in this kind of system, one of the only things you can do is literally do a comparison of two distributions. You can compare data you have from the data you observed as one distribution, and you can simulate from your model and use that as another set of data, and you can do that. So this is what will be the kind of principle of learning by comparison. And so we'll try and use this comparison to drive learning and to make statements about parameter learning and estimation. So here's a little diagram that just summarizes, in general, one way of seeing all the different solutions for learning by comparison or density estimation by comparison. Because you have this two distributions which you need to compare, you can either compute the ratio of these two distributions, and when the ratio is 1, then you've actually learned the data distribution, or you can take the difference of them, and when the difference is 0, then you've also learned the distribution. So there are many ways. We have a long literature about figuring out how to compute probability ratios or probability differences. And the one that we're going to look at in this class will be about class probability estimation. And maybe earlier you saw about MMD and moment matching kind of methods, and we'll discuss just a little bit about these at the end. So learning by comparison always has two steps. There's first a comparison step, which is where you do a hypothesis test, or you come up with some way of comparing two distributions. So you build this auxiliary model, and this auxiliary model is the thing that will help you make a statement about how currently two samples of data you have differ from each other or are similar. And once you have this auxiliary model or this comparison model, you can then do estimation. Based on that difference, you will then adjust your parameters so that you can make the distributions match better. So everything, all of these methods can be sort of thought of in this two-stage process like E and M, comparison and estimation. So let's just build a few tools and do a little bit of a derivation. So we're going to focus on the density ratio case. I'm going to compute the ratio of P divided by Q. I don't know P, but I do know Q because Q is a model I have that has some parameters. This is Bayes' rule, our favorite rule, and we're just going to need that because Bayes' rule helps us manipulate all probabilities. So I'm going to combine two sources of data. I have x hat, which are samples from the real data, and I have x tilde, which are samples from my model of the data, which I can use. So I'm going to assign some labels to these data. Everything that was real, I'm going to assign +1 to, and everything that was simulated, I'm going to say is the negative class, and assign a -1 to. So that's the real data versus the simulated data. And now there is an equivalence. So basically, the probability distribution P star of x is equivalent just by this modification or writing that I wrote, is that when I condition on the label 1, I get data which is from P star, and when I condition on the label -1, I get data which is from the Q distribution. And so this is the basic set of tools that we're going to try and compute this density ratio. So let's just do it together. We have this ratio, and I'm going to replace it by the ratio of the conditionals, which is equivalent. Now I'm going to apply Bayes' rule to both the top and the bottom. So I'm going to do the Bayes substitution. And the Bayes substitution is very simple. And now there are going to be lots of terms that can cancel. The P of x's cancel. And I'm also going to cancel the P of y's and assume that the two samples had equal probability. But if you sample them differently or in an imbalanced way, then you will be able to keep the proportions through this marginal probability. And then what you'll get is that effectively this density ratio is equal to the ratio of two conditional distributions. And what this says is effectively, if you wanted to compute the density ratio, all you need to do is build a classifier that helps you distinguish between samples from the real data versus samples from my model. Right? So this is now how you do density ratio estimation by classification. There are several other ways of doing this. So we'll fix that. So this is a principle, if you check in the elements of statistical learning by Hastie and Tibshirani, that they will call unsupervised as supervised learning. And now you see exactly why, because all I need to do is build this classifier of data, which is the supervised learning part. And so I can assign a scoring function to this, and of course you can choose any scoring function, and once I decide the scoring function d, the probability of the negative class is 1 minus that. Then, because you can choose any scoring function, and I want to build a classifier, it's very natural to use the Bernoulli loss or the log loss, depending on what you call the scoring function. The Bernoulli loss is always this. It's an expectation under the real data of log of this scoring function, and expectation under my model of log of 1 minus of the negative class. Of course, you can use any proper scoring rule can be used, so you can use the Bry loss, which is the squared loss, or any other kind of exponential losses. And then you do an alternating optimization between the parameters, sorry about this, between the parameters phi that you want to learn there and the parameters theta of the scoring function. So just to reiterate, there was the first step, which was the comparison step, and the comparison step happens through the scoring function d. And then there is this estimation step, and the estimation step is by phi. So when do you use this kind of a setup? Well, you will do this particular thing when the model that you actually have, x, if that's generating the data, is differentiable. And as I said, you can use any proper scoring rule. And this kind of a principle has lots of different names. As I said, they call it unsupervised and supervised learning. In other kinds of more economics, you will call this a continually updating kind of estimation. If you look in the more Bayesian statistics under ABC, approximate Bayesian computation, they call this kind of principle classifier ABC, and of course generative adversarial networks, which is very popular in machine learning these days, uses exactly this principle. So let's talk a little bit about generative adversarial networks. In generative adversarial networks, you have a generative model which has the following generative process. You can sample data from a prior distribution Z. It can be any source of prior distribution. Then you have a deterministic function f, which transforms that latent variable x, z into the actual data you want to see, whether that's images, video, temporal data, volumetric data, etc. So you can easily get these samples xgen just by simulating from that model, and if you have a data set, then you have x ops. So this is what they call DC-GAN. So this function f is itself a convolutional neural network, full convolutional neural network, and then there's lots of different architectures. And almost one of the most important things of getting this kind of a process to work is to get these architectures correctly. But once you get them right, you can do really powerful things. Again, the loss that we will use for both the joint loss is that Bernoulli loss from the classifier-based approach that we described before. And the alternating optimization, which is the same continuously updating optimization that we mentioned, just does a minimization on phi and a maximization on. So again, the comparison loss that you get, this is how you update the discriminator, as they call it, or this scoring function d is just to take the gradient with respect to theta. Because everything is differentiable, this is very easy to do in TensorFlow. And again, you get the generative loss. Again, you just extract from this thing everything that's dependent on phi. And how you actually do this is then you apply that pathwise derivative that we spoke about earlier. How you will do this, you can see Q can actually be re-represented through this generative process. So there's the kind of function that we were looking for, that transformation function. So we'll rewrite this expectation under this base distribution P of Z. Then the function goes into X, and then that's how the pathwise derivative operates. And so that's basically the principle of GANs. And then you can do all sorts of GANs now. You can see, well, why use this log loss? Well, when you can use other kinds of losses, boosting losses, exponential losses, Breyer scores, etc. Are there other ways of deriving these alternative losses for generative models? Are there other kinds of gradient estimators that you can use? In the choice of the function f, can I do other things other than convolutional network? Can I condition these distributions in other ways? This is how the work that we've done in the adversarial networks landscape. I just want to end with a more recent way of thinking that many people are exploring. In the most generic case, when you want to do comparison of data set, there exists a theory, a very powerful theory of integral probability metrics, which is how we can compare to distribution. And the generic theory again says you can build some function f, which is related to this kind of comparison we were talking about, and use that function f to make statements about how two distributions are related. How distribution P is related to distribution Q. And that function f is the equivalent of that discriminator, that scoring function that I showed you in the previous slide. So this function f is sometimes called the test function, or witness function, or crit. And there's a lot of work now in how we choose this function f. If you choose the function f as a classifier, like we did in the previous case, then you will get a classified two-sample testing. The function f can be Wasserstein, total variation, MMD, Kramer, and it's a really amazing space to work in to think about how integral probability metrics, dual functions, these variational formulations can be used to do learning, how that even relates to likelihood principles that we have in other kinds of estimation, and then to bring these two kinds of things together. Okay, so this is the last section, and then hopefully we can take some questions. I just wanted to show you how everything we've thought of up to now, is related. You can use that in many other ways. So I just wanted to make a little bit of a connection to policy learning, because all of policy learning is basically a problem of generative modeling. So when you deal with an environment takes an action A, and what you can get out of an environment is a reward, or you can observe something from the environment. The reward is a function of the state and the action that you chose. And the environment is something that is not differentiable. You don't know things, but you can observe its output. Of course, we can rewrite this because we have probabilities to say that, well, this allows us to observe some kind of probability over returns or rewards of some kind of internal scoring function. If you just apply the variational principle to this kind of probabilistic model with the prior over actions, you will get this kind of free energy. It's an expectation, and what was previously called Q is now going to be called pi here, of some log likelihood or log scoring function minus the k out. So what was previously called the Q distribution here, we'll call it the policy. The k out is the same, and this is the k out between a prior and whatever your policy is. So in the picture, again, the generative model is a prior over actions. That action goes into an environment which you do not need to know. You don't need to learn the generative model in this case, and then what you can observe from that is rewards. And then you want to do an inference, so you will take states and actions as an input. Through your policy, you will then learn a policy. So even this kind of is the principle of amortized inference. Then if you want to do a policy gradient update, as I said before, now you don't know anything about R, so the gradient estimator you need to use is the score function gradient estimator. And in RL, that will be called the reinforced algorithm. And if you choose the prior over the actions as the uniform distribution, well, the KL between any distribution and the uniform is the entropy. So then this recovers what they call the policy gradient algorithm with the entropy penalty. So that's basically all I wanted to show you. So there are many other ways of thinking about generative models in the space of policy learning. If you know algorithms like relative entropy policy search, you'll be able to derive an EM algorithm from this same framework. There's a lot of work connecting now adversarial learning to imitation learning that was presented yesterday at the workshop. Reinforced variational inference is another kind of framework of thinking about how policy learning affects it. This kind of thing has many different names. In other kinds of literature, they call it planning as inference. When we studied it earlier on, they were called variational MDPs. If you look more in control theory, all of the theory of path integral controls is expressed in this kind of framework, and the tools that we developed and that we discussed together today can be used in that setting. So, okay, that's the summary. We initially started off thinking about why you'd be interested in generative models, and we are extremely excited about generative models because we think they have roles in almost every area we can think of, whether that is in products, whether that is in science, or whether that is in AI and reasoning. Then we looked at probabilistic deep learning as the tool and then foundations that we will think about building our models. We looked at the types of generative models, in particular fully observed models and latent variable models. We looked at variational principles as one kind of way of learning about data and models. We then spoke about building richer distributions through various ways, in particular normalizing flows. We spoke also about amortized inference as a way of scaling up our inference to large data sets. We spoke about stochastic optimization and different kinds of ways of building gradient estimators. And then we spoke about a different principle for learning, which is learning by comparison. And this together, I think, is a good representative state of the art of generative models, but there are lots of challenges remaining. How we can scale to even larger images, videos, multiple data modalities, whether we have text, when we have images, when we have video, when we have sound. Evaluation continues to be a challenge, discrete latent variables, robustness, coverage of the density so that we don't underestimate and have bias in our models calibration, parameter uncertainty, principles, foundational principles. But we think there's still a lot to do, and we thank you for your attention. So if there are any questions, if you come up, we're happy to take any questions you have.
So you mentioned that a large number of components, and even as it is when you think of deep learning, right, many people have a feeling that you need to know the magic. You even said at some point, if you get it right, it's very hard. So how tough is it to get it right when it comes to that? Like, do you have to be DeepMind to get it right?
GANs are a place where we now have a lot of expertise, but it is true that there the challenge is that optimization is very hard because it's unclear what the right losses are, how you should do the optimization. But now we sort of do know through the literature, not just what happened at DeepMind. We've not done even that much in general, but the choice of the architecture does matter quite a bit. You do see there's a lot of hyperparameter tuning that needs to happen. The choice of the optimizers is important. So in that particular space, it can be very hard to get working if you want the best kind of generation possible. But I found them not too hard to get working. So with what you have in the literature, you can easily reproduce all of that, get started, and then build up from there and go forward. So I think we have learned a lot.
I have a question. Is the generative models easier to overfit compared to discriminative model? I'm asking about the overfitting problem of generative models.
Yeah, so the people on the back cannot hear, so it's a question about overfitting. How does overfitting with generative models relate to overfitting in classifiers, for example?
Yeah.
Of course, they can always overfit. If I take MNIST and I take a very simple NLP VAE with 100 neurons, and I take, let's say I take only 15 digits of MNIST, and I train this model, it's going to memorize exactly these 15 digits, and it's going to generate them perfectly. So it's quite easy to memorize a small data set with these models. Now, there are a few things that are different when you train a classifier, particularly in the case of models in the family of Gration encoders, is that there is a lot of the gradient estimators that you use, they have a lot of noise because it's a Monte Carlo approximation, it's a gradient estimator. It's unbiased, but it's still, even though we use all these tricks to reduce the variance, it's still quite a high variance gradient. And this naturally acts as a regularizer in these models, but it doesn't prevent overfitting. So when we apply this to some data, we always do the standard controls, which is we track the likelihood and hold our data and test set and validation set, and try to do our best to control these things. One thing that we don't control all the time, but we should, but we are trying to move towards that, is to control, as I said, for the complexity of the model itself. So almost no one in deep learning controls for that. But some people are starting to provide algorithms that makes this viable, where we can provide crude but better than nothing, better than point estimates approximation to, for example, the posterior over the parameters of a classifier or a generative model. And this also improves a little bit on the overfitting, because now when I compute the score of my model, this score is also going to know about the number of parameters inside this model, and I can more properly compare it to other models. But this is still something that we don't know how to do for all the models, and it's still quite tricky to do joint inference on all the latent variables in a very large generative model. So, yeah, just to summarize, yeah, you can overfit. Maybe it's not as bad as in a classification domain, but it's definitely a problem that we must control for.
What are your thoughts on choosing priors for these generative models? On one hand, it seems like as we make the model deeper, it can do anything it wants to the prior. But on the other hand, there's a recent paper saying like gauge or bad matching the marginals and things like that.
Well, that's an interesting question. Mathematically speaking, I can take a simple univariate Gaussian and transform that into the distribution of all natural images. So there's no limitation in principle of what I choose as my prior for this model. I could choose any density I want. Now the question is, will you be able to optimize the model to produce ImageNet samples if I give you, it starts with a single Gaussian sample? Probably not. So there is a complicated interaction between the choice of the prior and how well you'll be able to optimize this thing. And this is, we do that through experimentation because it's very hard to know in advance what's going to happen. Things, for example, making little changes to the model, like replacing the Gaussian by a uniform in some cube, or replacing the Gaussian by Laplace, etc. This has very little effect because after one or two layers of, let's say, relu nonlinearities, this can become almost anything, and the model has pretty much erased the identity of the original priors. So I don't think from both a theoretical perspective and both from an empirical perspective, the choice of the prior over this latent is so important. Unless there's something else you want to do with them. So, for example, if you want them to be sparse because X reasons, you want them to be interpretable in some sense or have some particular structure, then it will make sense to put some more structural prior there. But from the pure point of view of modeling the density of the data at the bottom, it makes very little difference. But of course, there's still some interaction between this choice and how the optimizer can find the reasonable solutions. And maybe related to that point is because, as Shakir explained, we can do these coordinate transformations inside the model, right? So what we actually call latent variables in this model should not be taken as an absolute definition. I can change my coordinate system inside this model such that what before was inside my deterministic layer is now a latent variable, and what before was a latent variable now is just part of my deterministic computational graph. And there's infinitely many such coordinate transformations that would result in exactly the same model. So that's why we should be a bit careful when we try to interpret these latent variables, because I can always find a coordinate system where any node in my computational graph is a latent, and I can always find another coordinate system where that thing is not that node is not a latent variable anymore, but just part of the computation. So this is another related aspect that we keep in mind when we build these models.
Thank you.